solving chemical problems. There's just no way around it that chemistry is full of word problems or story problems. We're not usually going to just give you math and ask you to do the math. We give you a setup, a problem, and we ask you to solve the problem. Most students don't have trouble with the math. What they have trouble with is looking at these words and knowing how to pull the numbers out and how to stick them into an equation. Once they've got the equation, everything's good. It's the interpretation, the application of it. But this is why they made you learn math, because you need to use math to solve actual problems. You don't just need to do math for math's sake. So we're going to learn how to do unit conversions, and most of the chemistry problems really go down to unit conversion problems. There are some that will require specific equations. Sometimes students feel more comfortable with those because they're like, ooh, that's something I can grab onto, that's an equation, and I could do things with that. But many other problems, there is no specific equation. So I'm going to teach you how to solve problems, not how to do specific little tasks. So units are awesome. This is probably the most important thing and the most useful thing I learned in all of high school was how to do dimensional analysis, how to convert units. It saved me in physics, in chemistry, in high school, and then I used it in college, and I use it to save money on my cat's flea medicine. I mean, there's just all kinds of places you can use it. Dimensional analysis is using the units as a guide to solve the problem. Okay? We should always include units. And they act like variables. They can be multiplied, divided, canceled, just like x's and y's. And so we want to just always, always, always include the units. Some students are like, I just really hate writing stuff down. Well, the thing is, you need to learn how to write stuff down. And then maybe in the rest of your career, you don't have to. But there's a lot of places where, at least occasionally, you need to be able to communicate with a pen and pencil, or a pencil and a piece of paper, really. Just a pen and pencil, like, oh yeah, here's what. Can I really do much with just these? Without any paper? This is just some random thought I had. You need to be able to write things out so that you can communicate with someone that's not actually standing next to you. So that's what we're going to learn. So what we often call a unit equation, you might call them conversion factors, the things you look up on a table. It's just a statement of two equivalent quantities. An example is 2.54 centimeters is equal to 1 inch. And what that's saying is this length, we can call it 1 inch, or we can call it 2.54 centimeters. It's the same thing no matter what we call it, right? We can take that unit equation and make it into a fractional quantity by dividing. So if I take 2.54 centimeters equals 1 inch, and I divide both sides by 1 inch, when I do the same thing to both sides of an equation, it's still equal, right? And then we could do a little simplifying. What's 1 inch divided by 1 inch? It's 1. Anything divided by itself cancels to 1. So this is equal to 1. So 2.54 centimeters per inch is numerically equal to 1, which means that if I multiply my inches by this factor, I'm really multiplying by 1. I'm not changing the size of the measurement. I'm changing the unit. We can make another factor by either inverting that one or think of it as dividing by the other one. Divide both by 2.54 centimeters. And now the centimeters cancel out. 1 inch per 2.54 centimeters is also equal to 1. So in dimensional analysis, what we're going to do is we're going to take the unit that we have, the measurement, and we're going to multiply by things like this that are equal to 1 so that the units will cancel out and we'll get the unit that we want at the end. So most problems are going to take this general form. You're given some information, you're going to multiply by one or more conversion factors, and then you're going to get the information that the problem's asking for. Or as an equation, it would look like this. The given unit times this relationship of the desired unit over the given unit gives you the desired unit. So let's do an example. How many centimeters are in 12 inches? Well, what unit am I given? It's the one with the number. Inches, right? So I'm starting with 12 inches, and what am I trying to find? Centimeters. So I'm going from inches to centimeters. So I'm going to start with my 12 inches, and then I need a conversion factor that relates centimeters and inches. So this is what I call a conversion path, and it's not much of a path, it's just one step, but they'll get a little more complicated. There's one arrow, and each arrow tells us we need a fraction. So I've got inches. I want the inch unit to go away, so that means I'm going to divide by inches, because then inches are going to cancel. And the unit I want to get is centimeters, and so I'm going to put that on the top. And then I have to figure out where the numbers go. Well, in case we forgot, 2.54 centimeters is equal to 1 inch. So I put the units in here first, and then I go looking for the relationship. One of these is going to go on the top and one's going to go on the bottom, and the unit I wrote in here tells me where it goes. So 2.54 centimeters. Well, centimeters is on the top, so I'm going to write the 2.54 on the top, and inches on the bottom, so I'm going to write 1 on the bottom. And then to do this on your calculator, you enter 12, multiply by the top, divide by the bottom. If you have more, you just keep going. Multiply by the top, divide by the bottom. Now, obviously, multiplying or dividing by a 1 isn't going to change anything. So if you want to skip that, you can. But if you're one of those people who's like, no, it says divide by 1, you go ahead and divide by 1. It's fine. So 12 times 2.54 is 30.48. And the only unit that's left is centimeters. Any questions? Here's a review question. How many sig figs should the answer have? 2. So 12 inches, it's a whole number, so it's tempting to think that it's exact, but it isn't because you can't count inches. That's a measurement, 2 sig figs. So the answer has 2 sig figs, and it would be best written as 30 with a decimal point. That's not best. It would be best written as 3.0 times 10 to the 1 centimeters. So this is the general strategy. I've been listening to podcasts because I drive back and forth between Wrigley and Fresno. It gets kind of boring. So I've been listening to some podcasts. There's some really good ones out there. And one of them I thought was super, super interesting. This guy had done really, really well in high school, and he comes to college, and he's going to be an engineering major, and he's studying and stuff the way he did in high school, and he's failing his engineering class. And he's like, what's going on? And so what he realized is that he was trying to learn how to do this problem, how to do that problem, how to do that problem, memorize all of the equations, not really understanding them, but just, trying to remember how to do all the problems. And then that's really hard to remember. This was a podcast about sometimes less is more. And so about halfway through the semester, he decided to change his strategy, which is a good idea. If your strategy isn't working, it's a good idea to change it. And he decided to focus on understanding the ideas and learning how those equations worked with each other. Understanding how the equation worked. And then he could see how he could derive all those equations that he needed in just a couple of steps. He didn't actually have to memorize all of them. And he got the highest score in the class on that exam. He just changed how he was thinking about it. And I thought, oh man, that's what my Chem 1A students really need to understand. What we want to do is we want to learn this general strategy. And we want to understand what we're doing. When I'm doing it up here, sometimes students say, well, this looks so easy when you do it. Well, it's because I've been doing it since before you were born, right? It is easy for me. But the first few times I did it, it wasn't easy. It's not easy until you get it, right? How do you get it? By trying and failing. You make mistakes, you get them corrected, you learn, okay? If you keep at it, you will get to that point where the light comes on and you see how it works. Once you see how it works, it's very easy to remember. You just have to push through and struggle through. It's going to take a lot of effort, but you're all capable of doing it, okay? So when we're working on the worksheet here tonight, if you don't understand what's going on, maybe it's like, well, somehow, my neighbor got that answer and I got the same answer as right, but I have no idea how I got it. Why does it work like that? Ask me, okay? I'm happy to explain it to you. That's what I'm here for. This is the general strategy. So you start with what you're given, right? Write down the numbers and the units. Sometimes you'll have units that have the word per in them, like grams per milliliters. That should make you think, you know what, that might be a conversion factor. Just kind of keep that in my head. Then you want to figure out where you're going, the end point. What unit are they asking us to find, right? And then you figure out a way to get from where you are to where you're going, right? You might have to go look up some conversion factors. And just like when you're going somewhere in real life, like I went to the Stanford Mall, and I remember, I was supposed to meet somebody at Starbucks. So I parked in some random place, and I walk up to the mall, and there's this nice sign, with a map, and it says, you are here. Good. That's the first thing I need to know. Where am I? And then where do I want to go? I want to go to Starbucks. Okay, now I need to figure out, how do I get there? Well, I could go this way, or I could go that way. I could go all the way around the outside of the mall, but that'd be kind of dumb, right? But there's different ways. And what might make sense to you might not make sense to someone else. But you figure out, how am I going to get there? And at least initially, you should write it down. That's the units with the arrows in between. Once you get that, then it's very, well, I was going to say very easy. It's much easier to do it. That's really the hard part. Okay, so you solve it, you follow the plan, use your calculator. Okay, don't do math in your head. I mean, it's great if you're good at that. My husband's good at that, and he's like always estimating things, and I'm just like, stop, you're hurting my head. Just let me do a calculator, it's in my pocket. Don't do mental math and make a mistake and get the answer wrong when you've done all this other good, more sophisticated chemistry work, and you got it wrong because you added wrong. So use your calculator. Do it twice. If it's important, do it twice. And it's one of the reasons I want you guys to do the calculations when I'm doing them in lecture, so I don't have to do them twice in lecture. Do it twice, punch it through on your calculator, write down the answer, clear it, punch it through again. Did you get the same answer? Good sign. Not a guarantee, but good sign that is correct. What if you get a different answer? Well, write that one down, clear your calculator, do it again, go for best 2 out of 3. It's very easy to make a mistake in your calculator, right? You thought you pressed the decimal point, but it didn't register. Or you accidentally got 2 2s or something. It's so easy to make a mistake like that. When you do it the second time, you're very unlikely to make that same random error again. And so it'll show up that you've got 2 different answers. The last thing is look at your answer and ask if it makes sense. Sometimes there's like, I don't know if it makes sense. Can't tell. But a lot of times you can. Like if you're calculating how tall the basketball player was and you ended up with 7 meters, does that make sense? No, that's impossible. Something went wrong. And we should always be writing things down, or writing out our work. And the wonderful thing about that is you get the wrong answer, you don't have to start from scratch. You can go back and see, written on the paper, what your plan was. You can find the mistake and fix it, okay? And you'll learn a lot more that way also. Okay, so we're going to do some examples here. Convert 288 centimeters to yards. Well, what am I starting with? Centimeters. And what am I trying to find? Yards. This one's pretty straightforward because there's hardly any words. Right? When there's a whole paragraph, it's a little more confusing. So I'm starting with centimeters, 288 centimeters. That's my start point. And I want to end up with yards. And now I need to figure out how am I going to get there. Did you guys watch Dora the Explorer? Yeah? One of these days, students are going to say no. It'll be sad. So for those of you that did, I know not all of you did, Dora the Explorer, she would have this problem where she needed to get somewhere. Like she was here and she needed to get to the snowy mountains. And who do you call when you don't know which way to go? The map, right? So this is our path. This is our map. And the map comes and says, we'll go over the stony bridge and under the shady trees and up the scary stairs or whatever. Right? It was always 3 things, wasn't it? And then they would chant it, right? So that they could remember. I guess they couldn't write stuff down in cartoons. That's what we're doing here. I'm starting at centimeters. I'm trying to get to yards. How can I get there? For those of you that didn't watch Dora, think of this as you're on one side of a creek and you're trying to get to the other side without getting your new shoes wet. And there's some rocks that you could step on. And it's like, well, I can't jump all the way across, not that good. Not sure if I can make it to that one. I think if I went to this one and that one, I could get over. That's the kind of thing we're doing here. We're strategizing. How can I get there? And the thing is, we need to use units that we know the relationships for, either in our heads or that we have available to us. Now, can you get Google to give you the relationship between centimeters and yards? Yes. Yes, you can. Does that help you learn the process? No, it doesn't. So that's why I say try to limit yourself to that unit list that's in the textbook. Okay, so here we've got centimeters, a metric unit, and yards, an English unit. I'm going to have to transition somewhere from metric to English. So kind of keep that in my mind. And I'm thinking, well, centimeters, what can I convert that into? Inches, we were just talking about that, right? So I could convert that into inches because I know there's a conversion factor even if I can't quite remember what it is. What's the relationship between inches and yards? Feet. Yeah, there's a unit in between. Feet. And then feet to yards. Now, some people might say, well, I know that there's 36 inches in a yard. Well, great, skip the feet. But somebody else might not know that. So this is the path we come up with, centimeters to inches to feet to yards. So this then tells us how to set up our equation. We take what we're given here, 288 centimeters. There's 3 arrows, right? 1, 2, 3. There's going to be 3 fractions. 1, 2, 3. What units go in here? Well, it's the units in the path, right? Centimeters to inches to feet to yards. I can just hear Dora saying that, right? Centimeters to inches to feet to yards. I'm just going to copy those down onto my equation, right? So I have centimeters. The next one is inches, feet, and yards. So once we have the path, copying that down, that's not too hard, is it? Now we need to figure out what unit goes in the bottom. It's the previous unit. I want centimeters to go away. So I want to divide by centimeters so it'll cancel out. So here I'm going to divide by centimeters. And then those are going to cancel. And so here I'm going to have that unit, inches. And the inches are going to cancel. You don't want to scribble them out because you still need to be able to read them. And what do I want down here? Feet, right? I am letting the units guide me, okay? I don't ever have to think, oh, am I supposed to multiply by 3 for the feet and the yards or divide? You don't have to think about that. You wrote the units out. They're going to tell you where to put the numbers, right? Because what's on the top has to equal what's on the bottom. So since we're just getting started, I'm going to write those unit equations out. So 2.54 centimeters equals 1 inch. That would be something you'd look up, right? 12 inches equals 1 foot. 3 feet equals 1 yard. So for this factor, inches and centimeters, I'm going to keep the number with its unit. So centimeters on the bottom, that means I'm putting the 2.54 on the bottom. And 1 is on the other side with inch, 1 goes on the top. So here I have feet on top and inches on the bottom. Where do I put the 12? Bottom, with its unit. See, it's 12 inches. Where's the inch? It's down here. That's where the 12 goes. And on the other side is 1 foot. Except it was 1 F. I don't know what happened to the T. There it is. And then 3 feet to 1 yard. So here I've got yards on top, feet on the bottom. 3 feet. Well, the 3 goes with its unit. So I make a path figuring out what relationships between these units, how can I get from one place to another? And then I use that to make my equation. Number of arrows tells me how many fractions. These are the units that go on the top. I take the previous unit and stick it on the bottom. Once I've got all my units worked out, either These are written down, they're in my head, or I'm looking them up. And I take the number with its unit, and I look, well, where's that unit? It's down here. So the 12 has to go on the bottom. Because we wouldn't want to say that 12 feet is 1 inch. Because that's not at all true, is it? What's on the top is equal to what's on the bottom. So now we get out our calculators. And I've got 288. I'm going to multiply by the top times 1. You can skip that. Divided by 2.54 times the top, divide by the bottom, divide by 12, times the top, divide by the bottom, which is 3, and press equals. Don't multiply all the numerators and multiply all the denominators and write stuff down and divide it. Every time you write something down, you could make a mistake. Every time you type it back into your calculator, you can do a mistake, right? Just way more opportunities for mistakes. Takes longer too. So just go left to right, top to bottom. Times the top, divide by the bottom. And so my calculator is giving me a long mess of digits. So I'm going to think, as I write this down, how many sig figs is my answer supposed to have? 3. See, 3 or 4 is usually a good guess. Here, the number that I started with had 3. This is an exact conversion, because it's the one, because I told you it was. This is exact, it's within the English system. This is exact within the English system. And what that means is I don't have to look at those. I don't have to look at them at all. They don't matter because they're exact. So because all of these are exact, I started with 3, I'm going to end up with 3. So then as I'm writing this number down, I'm thinking I need 3 sig figs. So 3.14, that's my third one. And then I'm going to write down 2 extras. 9/6, and the unit is yard. And now I'm going to round it. So when I'm rounding, I'm going to look at the next digit, and that's going to tell me whether I need to round the underlined digit up or not. Here the next digit is 9, so this is going to be 3.15 yards. Any questions? So on question 12 of the worksheet, what I want to see, I want to see you write it out like that. If you want to write the path out, if that's helpful to you, go ahead, but I'm not going to require you to do that. You don't have to write these down. But when I talk about showing your work, this is what I mean. And I really would like to see the unrounded number. If you want to write all the digits, that's fine. But if you're lazy like me and you don't want to write all of them, just at least write 2 extras and then round it. Because if you go back and look at this later and you realize, oh shoot, that was supposed to have 4 significant figures, but you just wrote down 3.15. Then you have to do the calculation again. And if you didn't write down the work, then you have to start at the beginning and solve the whole thing over again. So sometimes students are like, well, it takes so long to write that all out. Well, in the beginning, it does take a while. But it helps your thought process, and it'll get faster, and then it'll actually save you time. Because if I needed another digit, I could go back and say, oh, that should have been, the way this would round it should be 150. Or you may realize, I need this for another calculation. I'm not supposed to round if I'm using it for another calculation. Well, 2 extra digits is enough to keep you from having rounding errors. That's just kind of my rule of thumb. And honestly, this second digit that you write, the second extra digit, it doesn't even matter if you round it up or down. You can just write it down and not even look at the next one. It doesn't matter, it's not going to affect anything. It's just this one when you round that you have to worry about. Any questions? 3.15 yards. So we're going to do some more examples. Convert 9,255 cubic centimeters to gallons. Did I put anything? No. Oh, yeah, I did. So what unit are we given? Centimeters cubed. And what are we looking for? Gallons. So I've got 9,255 cubic centimeters. And then just, I don't know how many arrows I'm going to have in there, so I'm just going to, give myself some space and put gallons over here. Sometimes they get kind of long. Sometimes it's only one and you just have a really long arrow. It's fine. Okay, so I've got cubic centimeters and I've got gallons. And I put this in here because this is something we'd probably go look up. That's not something I remember. But I know that you can convert gallons to liters. So looking through that table in your book, this is one of the conversions that's there. When you're finding this path, sometimes when you start at the beginning, you're like, I don't know, I have no idea. Well, you can go to the end and work your way backward. And then sometimes you kind of do from the end and from the beginning, and you just kind of meet in the middle. It's a puzzle. You're not supposed to just know how to do it. You're going to look at that and you're like, I'm not sure. Well, it's a puzzle, right? Solve it. Think about it. Figure it out. Well, gallons, when I look up here, I know the relationship between gallons and liters. So if I got to liters, I could get to gallons using this guy. So this is helpful because that's a metric unit of volume. This is also a metric unit of volume. Well, what's the same as a cubic centimeter? A milliliter. So I can change cubic centimeters into milliliters. Can I change milliliters into liters? Yeah. So there's my path. That is the hard part. Now we take our number with its unit, 9,255 cubic centimeters. Oh, that's an ugly 3. How many arrows? 3. 3 fractions. Where do I find the units for these? They're just here in the path, right? Cubic centimeters to milliliters to liters to gallons. You can just see Dora with her dorky haircut, right? How is your head even shaped like that? Cubic centimeters to meters to liters to gallons. What do I put in the bottom? Centimeters cubed. The thing from the top previously. And I'm doing that because I want those to cancel out. I'm like, okay, I've got one on the top and one on the bottom. Those cancel out. And here I've got milliliters. I want that to go away, so I'll put milliliters down here. And those will cancel out. And I want the liters to go away, so I'll divide by liters here. I crossed out all the units except gallons, and that's what I was trying to find. So now I put the numbers in. And it doesn't matter if you start at the beginning or the middle or the end. I've got this one right here staring at me. So 1 gallon. So 1 gallon is 3.785 liters. So down here with liters, 3.785 liters. Okay? I'm taking one side goes on the top, one side of the equals will go on the top, and one will go on the bottom. How do you know which is which? You already put the units in there. Milliliters and liters. Well, let's think about this. What does milli stand for? 10 to the minus 3. So if I have 1 milliliter, That's the same as 1 times 10 to the minus 3 liters, just like what we were doing with the units before. I can take this, and instead of writing milli, I can write the factor of 10. 1 milliliter is equal to 1 times 10 to the minus 3 liters. Now, some of you may be thinking, but a liter is 1,000 milliliters. Also true. Also true. And if you can remember that, you go ahead. But there's a fair number of students that if they don't follow this pattern all the time, they're going to tell me that a milliliter is 1,000 liters. Do you know how big a milliliter is? It's a cubic centimeter. How big is 1,000 liters? 500 2-liter bottles of soda. Is that the same as a cubic centimeter? No, you got the numbers switched, right? So the way I'm going to do this in lecture is we will never have a number like this and a prefix together. The prefix is on one side, and what it means is on the other side. And if you just always do it that way, it'll always be right. Thinking is good, but thinking can make you tired, and sometimes when you think wrong. And so my feeling with a lot of these problems is, how can I make there to be less thinking, right? So I can just do it and be done with it. So this is a pattern, the prefix on one side, what it means on the other, every single time. Okay, what's the relationship between milliliters and cubic centimeters? 1 and 1. And so, some people are like, well, duh, we didn't have to put that in there. Well, no, you didn't, and we see that now, but it's in there, so just leave it alone. It's fine. Okay, this number is in scientific notation. You need to know how to enter scientific notation on your calculator. I know that you can translate that into decimal notation and type it in, but when we get to Avogadro's number, which is 10 to the 23, you cannot, because your calculator can't handle it. And who wants to type in 23 zeros anyway? Yeah. Okay, so on your calculator, and get it out and actually do this. So 1 times 10 to the 3, you're going to type in 1, and then most calculators are going to have a button that says EE, or it might say EXP, or there's a few that say times 10 to the x. Not 10 to the x, times 10 to the x. So if you're not sure which one of these you should use, as soon as I'm done with this example, I'll walk around and answer questions. These things stand for times 10 to the. Okay, so all of these guys, times 10 to the. So I press 1, and as I push this button, I think times 10 to the, and I want -3. And so there's a button, it might look like that, a negative in parentheses, or it might look like a +/-. It's not the subtraction button. It's a different button. And then the 3. 1 EE -3. So let's see if we can all come up with the same answer here. So we've got 9255 times 1 divided by 1 times 1 EE -3 divided by 3.785 equals. How many sig figs? 4. So as I write this down, I've got that in my head. There's 4 sig figs. So I'm going to underline that one and just write down 2 more. 2.445 pounds. So any questions? Okay, let's talk about just the metric prefix things. I know I already did one of these, but this is the more instructions. So it's very easy to make conversion factors between the base unit, which is like meter, gram, liter, the thing without a prefix, just the unit itself, and the same unit with a prefix. So we've done that a little bit. So 1 kilometer equals, well, what does kilo stand for? Times 10 to the 3. So this is 1 times 10 to the 3 meters. Because kilo, ooh, that was scary. Kilo is just really short for times 10 to the 3. It's easier to write, easier to look at. So the prefix goes on one side. There's the prefix. The multiplier, the 10 to the something, goes on the other side, never together. Okay? Yes, you can do other things, but I'm not going to talk about them in front of everybody. Okay? Because this always works. And if you struggle with it, let's just stick with the thing that always works. Now, what if you have a conversion where both of the units have prefixes? And there's an example of that in the worksheet. So like this one, we're converting from centimeters to nanometers. Well, you could figure out the relationship between centimeters and nanometers. In my mind, that involves too much thinking, right? I wouldn't do it. It's easy to mess up. So I would look at this and say, oh, I have 2 prefixes. I'm going to just do that in 2 fast steps. So I'm going to go from centimeters to meters and meters to nanometers. And on the worksheet, I tell you in some of them, be sure I'm telling you right. I tell you how many steps, I even tell you the path. Like there's one like this, number 12D, converting microseconds to milliseconds. It says 2 steps, microseconds to seconds to milliseconds. You have to do it that way on this page. Okay? It's not the only way to do it, but I want you to do it my way on the page. Okay? For time's sake, I'm going to skip that one because we've already done some like that. Here's one with 2 prefixes. Convert 5.52 times 10 to the minus 5 centiseconds to microseconds. Like, why would I want to do that? Well, it doesn't matter. We have to do it. What are we starting with? Centiseconds. And what are we ending up with? Microseconds. Okay? So I'm just going to follow my same pattern I've been doing. I'm going to write down the number with its unit, 5.52 times 10 to the minus 5 centiseconds. And I'm going to microseconds. Both of these units have prefixes. I have 2 prefixes. I have this prefix and that prefix. 2 prefixes, 2 steps. And the thing in the middle is the unit without a prefix. So I'm going to go centiseconds to seconds to microseconds. It's much less thinking. It's ultimately faster, even though it's 2 steps. 5.52 times 10 to the minus 5 centiseconds. 2 arrows, 2 fractions. So centiseconds to seconds to microseconds. I take the first unit and put it in the bottom so they cancel out. And I take this unit and put it down here so the seconds cancel out. And then I'm left with that unit I wanted. Now I put numbers in. So if it has the prefix, it's one of those, 1 centisecond. And then on the other side, I'm going to write what centi means. Centi is 10 to the minus 2. You know, haven't memorized all those yet? You just go look it up in the table. Centi is 10 to the minus 2. Just write it in there. Here I have micro, the prefix on the top. So 1 microsecond. On the bottom, 1 times 10 to the what? What's micro? Negative 6. Did I have to do any hard thinking? The hardest part was just matching up the prefix with the multiplier, which as we memorize them, that'll get much faster. Okay, so do this one too, using scientific notation. 5.52 and EE negative 5 times 1 EE negative 2 divided by 1 EE negative 6 equals, and it says 0.552 microseconds. Like, well, that wasn't a whole bunch of digits. How many sig figs should I have? Well, my conversion factors are all exact. I started with 3, I should end up with 3. Any questions? The nice thing about the videos is you can go back and watch that over and over again if you need to. 0.552 microseconds. Oh, units raised to a power. You guys want to take a break? You want to plunge ahead? Nobody's saying anything, we'll just keep going. So units raised to a power. This happens when we're talking about an area or a volume. So we're going to build those conversion factors from the unit without a power. So if we want square inches to square centimeters, we're going to start with centimeters to inches. So that's the same one we've used before. 2.54 centimeters is equal to 1 inch. But these units are squared. So I need to square both sides, including the numbers, including the 2.54. So this will be 2.54 squared times centimeters squared is equal to 1 squared inches squared. Well, 1 squared is still 1, right? But 2.54 squared is 6.45. So I end up with 6.45 square centimeters is 1 inch. How many cubic centimeters are there in 2.11 cubic yards? Let's see. I'm going to do this one instead. This is more story. A vineyard. A vineyard has 145 acres of Chardonnay grapes. A particular soil supplement requires 5.5 grams for every square meter of vineyard. How many kilograms of soil supplement are required for the entire vineyard? Now, is that something that could come up in real life if you were a farmer? It could. Okay, this one's more involved, right? There's more story here. There's several numbers in there, and it's not as straightforward. Well, we read the whole problem. Now we're going to go back and look for the numbers. And what numbers do they give us? What units? Well, 145 acres. And then this one is all in words, so it's kind of funny, but grams for every square meter. That's grams per square meter. So that was given to us. And what do they want us to find? How many kilograms? So we've got two things here. I'm just going to write them down because that one's in words and it's kind of hard to look at. So I have 145 acres, and I have 5.50 grams for every is a different way of saying per, right? Grams per square meter. Grams per meters squared. Per how many meters squared? Well, per 1 meter squared. So those are the two numbers or two units that I was given. And it's not always obvious, well, which one do I start with? This is just a plain old unit, right? Acres. And this is one of those derived units. It's got per in it. This could be a conversion factor. That cannot be a conversion factor. So that's the one we're going to start with. So we're going to start with acres, and then we're trying to get to kilograms. And it's, well, whatever. Oh, I see, okay. I was like, wait a minute, there's no units raised to a power conversion. Yeah, there is. I'm just babbling. Okay. Any questions on how we got that far? Now, how can we get from acres to kilograms? This is not obvious. Well, we were handed something right here, right? So I could go from acres to square kilometers using that guy. So let's go from acres to kilometers squared. So that's some progress. This guy probably is going to get used in here because some of these questions are tricky, but we don't usually throw lots and lots of extra stuff in there at you. So you're probably going to need to use all the numbers. This relates grams and square meters. Well, I have square kilometers and I have kilograms. Well, could I get from grams to kilograms? Sure, we just learned how to do that. That wasn't too bad. This allows me to convert between grams and square meters. So from square meters to grams, and then can I go from square kilometers to square meters? Yeah, I can. That's the hard part. Making the path. Any questions? Now we're going to use the path. How many arrows? So it's got 4. Got 4 fractions this time. So 145 acres times acres to cubic meter, kilometers to cubic meter, sorry, I can't even read. Acres to square kilometers, to square meters, to grams to kilograms. Best not to actually say it out loud. Just copy it. Right? I'm just taking these units in order and putting them in here. And then I take the first unit and put it in the bottom here so it cancels out. And I take this one, I put it down there so it cancels out. Got all my units to cancel out. Now we put numbers in. Well, this one was given to us. So this is going to be the square kilometers to acres, and I'm just going to keep the numbers with their units. So 1 square kilometer 247 acres. I don't want to think about that one yet. What about this one? Well, that was given to us in the problem. This is not a conversion factor that you could look up anywhere because it only applies to this problem. But I keep the 5.5 with the grams and 1 with the square meters. Kilograms to grams. Here I just need to know, what does kilo stand for? I have 1 kilogram. That's 1 times 10 to the 3. Because you memorize it. Because you look it up in the table just because it is. Because somebody decided it. So now we have this units raised to a power that we have to deal with. So let's pull that out and look at it separately. Without the square, I have meters and kilometers, right? So 1 kilometer is how many meters? 1 times 10 to the 3. Kilo's the same here as it is down there. So we learned how to do that. What's different here is that the units are squared. The units are squared, so I square the whole thing, including the number. And the very common mistake is that students forget to square this number. So 1 times 10 to the 3rd squared, meters squared is equal to 1 kilometers squared, because 1 squared is 1. One of the issues is, I think, it looks like we didn't square this one. We did, it just didn't do anything to it. So I want to put 1 times 10 to the 3, the quantity squared, where meters is. Any questions? Pull out your calculator. 145 divided by 247 times, if parentheses make you more comfortable, go ahead and use those, 1EE3 squared times 5.5 divided by 1EE3. This should have 3 sig figs. So I'm getting 3228.7, and the unit should be kilograms. Did anybody else get that number? Yeah. If using the x squared button on this makes you a little nervous, I'm not sure if it worked out right. Well, let's do the calculation again, and instead of using the squared button, let's just put that in twice, because that's what it means, right? 145 divided by 247 times 1EE3 times 1EE3 times 5.5 divided by 1EE3 equals, same answer. Do I need to be careful when I round this? I'm rounding in the tens place. I need to be careful that I don't change the number. It's 3,000. I don't want to end up with 300. My grapes wouldn't do very well. So it's best to put this in scientific notation. So I'm going to put it in scientific notation. That would be 3.2, and I can round it at the same time because this is going to round the 2 up to a 3. So 3.23 times 10 to the, and I'm taking this decimal point and I'm moving it 1, 2, 3 places. 3,000 is a big number. I have positive feelings about big paychecks. Kilograms. When we're putting things in scientific notation, we're going from where the decimal point actually is. We're not starting from the end of the number. You're just moving the decimal point from here to always after the first non-zero digit. So we shouldn't have 32.3. It has to be 3.23. Any questions? Yeah.
It's okay if we just write, like when we're doing this one, it's okay if we just write it twice, right? Like
Yes.
instead of like using the fingers.
Yeah, if you're doing the squared or cubed units and you want to just put the factor in there 2 or 3 times, that's absolutely fine. Yeah, yeah. Okay, I think this will be the last one. So this, as the title suggests, density as a conversion factor. Most students have been taught D equals M over V, and you have a variety of little triangle things for rearranging it, and well, what if you need V, how do you find that, blah, blah, blah. My experience is that a lot of students aren't so great at rearranging equations, especially solving for a unit in the or a variable in the denominator like volume. You do not have to ever rearrange the density equation because density is just a conversion factor. The only time you need the density equation is if you're actually calculating the density. We did that. Density is mass divided by volume. That's the only time we're going to use that equation. We're not going to rearrange it. We're not going to look at triangles with D's and M's and B's and stuff. Okay, so backpackers often use canisters of white gas to fuel a cooking stove's burner. Well, that's nice. If one canister contains 1.45 liters of white gas and the density of the gas is 0.710 grams per cubic centimeter, what is the mass of the fuel in kilograms? So what are we going to ask ourselves first? What am I given? Where am I starting, right? It's the map at the mall with the little red dot. You are here. You've got to figure that out first. So 1.45 liters, and something else they gave us is 0.710 grams per cubic centimeter. Those were given. And what do we want? Kilograms. So I'm going to take both of these yellow things and write them down because we can only start with one, and sometimes we don't know which one to start with. So let's just write them both down. 1.45 liters. And this is a fraction, but it uses the forward slash. Because typing equations using a vertical fraction when you're typing is a pain in the butt. You have to pull out a math editor, and it really sucks. And that's why when it's typed, you usually see it like this. But when you're writing it out with your very own little hand, it's no harder to make it vertical. Make it vertical because then your brain will recognize it as a fraction. If you put it like this, your brain's like, denominator? What denominator? I just see a thing, right? And then people do crazy things and get answers wrong. So we're going to take that and go 0.710 grams per cubic centimeter. And then we might as well just extend that line. And if we wanted to put a number on the bottom, what would it be? 1. grams per 1 cubic centimeter. That's implied. Which one of these could be used as a conversion factor? The fraction one, right? Could this be used as a conversion factor? No, it's just a volume. This is what we're going to start with. So we're going to go from there, and we're going to try to get to kilograms. Well, let's give ourselves a little more room. So a clue is that we've got this here. Grams and cubic centimeters are going to be in the middle here somewhere. Well, cubic centimeters and liters are both units of volume, but I don't really know the relationship off the top of my head. Grams and kilograms, oh, we could do that one, right? One prefix, one step, right? So grams to kilograms would work. This relates grams to cubic centimeters. So to get to grams, we would need to start with cubic centimeters. Right? That's not something we just normally have, but because they gave us the density, we do know that. How can we get from liters to cubic centimeters? Milliliters. So here's kind of a hack. What's another name for cubic centimeter? Milliliters. So how about we just call that milliliters and call this milliliters? They are the same, right? Can we go from liters to milliliters? Yeah. Okay, there we go. You don't need the density equation. So I'm just doing dimensional analysis. I'm just going to do what I always do, 1.45 liters. I count 3 arrows. I have 3 fractions. Liters to milliliters to not cubic centimeters. We chopped that one out. To grams to kilograms. If you don't like this hack and you want to go from liters to milliliters to cubic centimeters, you go right ahead. There's nothing wrong with that. So liters comes down here, cancels. Milliliters comes down here, cancels. Grams comes down here and cancels. I have milliliters and liters. Milli is on the top, so I'm going to write what it means on the bottom because I don't want to put them together. So milli means 10 to the minus 3. I have 1 milliliter is 1 times 10 to the minus 3 liters. The grams per milliliter here is the density I was given. And we don't have to think about, was I supposed to multiply by the density or divide by the density? No, just make the units work. So the 0.710 goes with grams. 0.710 grams, 1 milliliter. Over here, I've got kilo on the top. I write what kilo means on the bottom. Kilo represents 10 to the 3. 1 kilogram is 1 times 10 to the 3 grams. So I've got 1.45 divided by 1 EE, negative 3, times 0.710 divided by 1 EE 3. 1.0295 kilograms. How many sig figs should it have? 3. I have a density and my starting number both 3. 1.03 kilograms. Any questions? There are density problems on the worksheet. If you are calculating density, you have to use the density equation. If you're calculating mass or volume, please try it this way. It really is much easier.